This conference will now be recorded.
Hello everyone, the topics that we are going to discuss today: uses of H2, and then we will start the new topic, which is water, physical properties of water, structure of water, and chemical properties of water. So uses of water, this is the topic with which we will finish the part of H2 gas. So chemical properties, how we can produce H2, physical properties of H2, everything we have finished in the last class, and now only the use part of hydrogen that is left, that we will finish now. So hydrogen, it is used in the manufacture of ammonia gas. So ammonia gas, as you can see from the formula, we need nitrogen and we need hydrogen. So nitrogen and hydrogen together, it produces NH3, and this reaction we have already discussed under the chemical properties of H2, where we have seen how hydrogen reacts with nitrogen. It produces ammonia, and for large scale preparation of ammonia, that means for manufacturing process, this method is used. Largest single use of hydrogen in the world is in the manufacture of ammonia gas. So it proves that its importance, largest single use of H2, hydrogen, not H2O. So it consumes about 2/3 of the world's H2 production. So you can understand 2/3 means most of the amounts of hydrogen that is produced all over the world, that is utilized for the manufacturing of ammonia. Now ammonia is also very important. Ammonia is used for the manufacture of other chemicals such as nitric acid, fertilizers, explosives. Fine. So this is the first use of hydrogen, manufacturing of ammonia, because ammonia is another important industrial chemical. Next use is methanol manufacture. Methanol formula is CH3OH. So CH3OH, hydrogen is there, but we also need carbon and oxygen, and the source is carbon monoxide. So for manufacture of methanol, this is basically industrial solvent. This is used in laboratory for as solvent for doing chemical reactions. So this methanol can be produced starting from carbon monoxide, oxide of carbon, and hydrogen, and we get CH3OH. This is the second application. Third one is metallurgy. In metallurgy, what we do, that is naturally occurring metal salts or ores, minerals. From this, we extract only the metal by removing the impurities. So there is a separate chapter on metallurgy. Now in metallurgy, what is the role of hydrogen? We know hydrogen has reducing property, and this reducing property is utilized in the metallurgy. So suppose any metal that is present in its oxidized form, that means with charge Mn plus. I am writing in general form, it may be 2 plus, 3 plus, whatever, but from this cation, that is positive charge, in presence of hydrogen, now it will be taking electron from hydrogen and it will be converted to the metallic state, and that we actually do in metallurgy. So different types of reducing agents are used, and one of these reducing agent is H2. So it is used to reduce many metal oxides to form the metals at high temperature. Example, you can see copper oxide, where copper is having oxidation state 2+, and in presence of hydrogen, now copper oxide is reduced to copper, which is the metallic form, and H2 is oxidized to water. Another example is tungsten oxide. Tungsten oxide WO3 in presence of 3H2, it is reduced to the metallic form, which is W, that is tungsten, and water is oxidized to hydrogen is oxidized to water, which is H2. Cutting and welding purpose. So cutting for that is cutting of different metallic substance, or welding. Welding means at high heat or pressure, when two parts of metals, they are fused and joined together. So for this large heat that we require, that may come from atomic hydrogen and oxyhydrogen torch. Oxyhydrogen torch, it is also known as hydrogen torch. So in this torch, what happens? The hydrogen gas in presence of oxygen, it produces a large amount of heat, and that is actually used for cutting purpose and welding purpose. Next use is reduction. Now reduction in metallurgy application also we have seen, but here by reduction we are basically talking about some organic molecule. Okay, so it can be used as reducing agent for different organic molecule. For example, unsaturated vegetable and animal oils. So in these molecules there is large amount of unsaturation, that is CC double bond, and fats. Now they are undergoing hydrogenation reaction. That means these double bonds that are present in these large molecules, oil molecule, fat molecule, now in presence of H2, there will be addition of hydrogen like this. So the pi bond is broken and there is formation of two new CH sigma bond. So now it is saturated. From unsaturation, now we are getting saturated compound, and for this purpose we are using a reducing agent H2. These saturated fat, they are called vanaspati or margarine. Now the hydrogen is used to reduce aldehydes also. Aldehyde means, in general, I can write the formula RCOH. So RCOH, and not only aldehyde, fatty acid. Fatty acid means it is containing some alkyl group. Now this alkyl group is long chain of carbon and hydrogen, and then there is carboxylic acid. So for this type of fatty acid, and then esters, that is RCOOR prime. So for all these molecules we can use hydrogen as the reducing agent, and all these compounds can be reduced to alcohol, which is ROH. Fine, in general I am writing the formula. Then what about aromatic compounds? If we have some aromatic compounds, that can also be reduced to the corresponding saturated compounds. Now suppose you have taken phenol. Phenol is having formula that is structure OH group attached to one of these carbon of benzene ring. Now when I am saying aromatic compound reduced in presence of H2, basically all the CC double bonds that are present, that will be now converted to saturated compound. So now it will be cyclohexanol. You can see all these double bonds are no longer present. Fine. So phenol to cyclohexanol. Then nitro compounds can also be reduced easily to amines. Nitro compounds, suppose I have taken nitrobenzene. So NO2 group is attached to benzene ring, and in presence of hydrogen and also some metal catalysts are sometimes used, they can be reduced to amines. So here in the benzene ring there is no change, only this NO2 now it is converted to, that is reduced to NH2. So these are the different examples of reducing agent. It is very versatile, that is different types of reactions, different starting materials we can use, and in presence of the common reducing agent H2, though other that is reaction condition may vary, sometimes metal catalyst may be required, but apart from that H2 is the common reducing agent for all these reactions that I have drawn. Okay, so this is the application which is mainly in chemical reaction as reducing agent. Then the next one is energy source. Now for energy source, normally what we use? Normally we use some fossil fuel and electric power. That is basically conventional energy source. Now it has many advantages. That is, hydrogen has many advantages compared to this conventional source. What is the advantage? If you use conventional source, the byproduct that is produced, that is not good for nature. It is polluting the nature. So that is why instead of using this conventional source, if H2 is used, it is basically clean fuel. Now why we are calling it clean fuel? Because now in this case the byproduct is only water, which is benign for nature. So when H2 is used as clean, it is clean fuel, and when it is consumed in fuel cell, it produces only water and it produces heat and electricity. But that is not very harmful for the nature. Okay, so that is why compared to the conventional sources, it is better. It releases greater energy per unit mass of the fuel also. If you compare with other fuels, not only that the byproduct is less harmful, but the other advantage is it releases greater energy per unit mass. So if you compare with other energy source, now you have taken common mass. So from common mass, you are getting more energy in case of H2. So that is why it is the advantage in comparison to gasoline and other fuels. Another point is reversible uptake of hydrogen in metals. That is metals, there is a reversible reaction with hydrogen, and that is the reason why we can make metal hydride battery. Metal hydride battery, it is rechargeable. So that is a very good point. Once the battery, it is we can reuse it. That is why it is rechargeable. You can charge it again because of this reversible reaction. So that is why we can make rechargeable metal hydride battery. So these are different examples that it can be used as energy source. Though it is not nowadays, it is not fully used as energy source because there are some other hurdles that we have to overcome. But still, it is a hope for us that we can replace the conventional energy source with H2 because it has some advantage. Rocket fuel. Hydrogen has been used as primary rocket fuel for combustion purpose with oxygen or fluorine, and it is favored as a propellant, though there are many different types of propellant, but it is favored for nuclear power rockets and space vehicles. So after uses of H2, basically we'll start hydrogen, we will start water, but before water, just one topic left, which is related to hydrogen, but it is not exactly hydrogen, it is basically hydride. Now what actually hydride means, that we already know. It is basically hydrogen atom carrying negative charge. We know when it carries positive charge, we call it proton, but when it is carrying negative charge, we call it hydride. Now there are different types of hydride, basically three different that is classification. If we do, there are basically three classes. So we will cover these classes, three classes in detail. Hydrides are a class of chemical compounds in which hydrogen is combined with another element. Now this another element, it is obviously carrying more, it is more electropositive in nature compared to hydrogen. So that is why negative charge will be over hydrogen. There are three basic types of hydrides. The first category is ionic hydride or saline hydride. The second category is covalent hydride. And the third category is metallic hydride or non-stoichiometric hydride. Okay. Now, how we are getting this classification? It is basically based on different types of chemical bonds. So what is the nature of chemical bond between the element, the other element with which we are having this hydride compound? So depending on the nature of bond with this other element and hydrogen, we are having these three classes of hydrides. But remember, hydride means hydrogen, there is negative charge. Fine. So first we will start with ionic or saline hydride. Ionic or saline hydride, from the name you can have some little idea. Ionic hydride, that means there will be ionic bond, right? So these hydrides are salt-like, and you can see the properties are just like ionic compounds. For example, a high melting, crystalline solid. So these type of properties normally we observe for ionic compounds. So that is why as we are calling it ionic hydride, so you will observe this type of properties. So here we have H minus ion and metal cations. So the other part, that is the other element, it is very electropositive metal, and mostly the elements are, that is these metals are very electropositive, though we know there are different types of metals. If you consider the periodic table, different types of metals are there, but here we are talking about electropositive metal. Now the most electropositive metals, they are residing in the S block, right? So in the S block we have group 1, and we have group 2. Group 1 is alkali metals, group 2 is alkaline earth metals. So now we have to consider these metals only. So for ionic or saline hydrides, here the metals are very electropositive. It is alkali metal or alkaline earth metal. But you have to you don't consider these two, that is Be and Mg, the first two elements of group 2. Now why we are not considering it? Because for these two metals there is some covalent character generated, and that is why these two are the exceptions. So except these two, rest of the metals you can have ionic hydride. So here an alkali or alkaline earth metal, they transfer electrons from metal to hydrogen. So as the metals are transferring electron, because we know when there is ionic bond, suppose I am saying there is ionic bond between A and B. Now ionic bond means one element is completely, it has lost electron, another element completely accepted that electron. For example, Na plus Cl minus. So this is basically ionic bond, positive charge, negative charge. So in this case also same thing, electrons are donated from metal to hydrogen, and we are having this H minus. LiH, BeH2, MgH2, they are more covalent in nature. So that is why for Be and Mg, you can consider it as exception. LiH, it is less covalent compared to Be and Mg. So, but still remember, though we are considering LiH under ionic, but still it is having some covalent. And better we do not consider these two hydride, BeH2 and MgH2. Look at the formula. Here the formula is Mh. Why? Because oxidation state of group 1 metals is +1 only. But when you are considering the metals from alkaline earth metals, that is group 2, now the formula is Mh2, that is BH2, MgH2. But if you are considering the metals from group 1, it will be NaH, KH, like this, or LiH, because oxidation state is +1. But for metals from group 2, their oxidation state is +2, so the formula will be BeH2, MgH2. So they are more covalent in nature, and see, they are polymeric in structure. It is not that they are having some crystalline solid, but they are polymeric in structure, which is mostly the covalent character. So that is why these are exceptions. Next point, when they are in molten state, these ionic hydrides, they can conduct electricity, and on electrolysis, they can even liberate hydrogen gas at anode. So see, when it is in melted condition, that is H minus. Melted condition means what? Now the metal ions and the anionic part is H minus. Now the metallic part, there is a cationic part and anionic part, they will be separated. We have melted them, they are in molten state. So in molten state, from this anion H minus, they can liberate this electron, and now H2 is produced. So electron is removed from H minus, and this reaction is occurring at anode. We know at anode oxidation occurs. So at anode oxidation occurs means H minus, it is oxidized to H2 and it is releasing electron. Next point, the H minus ion that is present in saline hydride, formula Mh, that means group 1 metals. They behave as strong base. And why they are behaving as strong base? It is because of the presence of the hydride ion itself. These hydrides, they can react instantly and quantitatively with the H plus that is coming from water, and it can produce hydrogen gas and hydroxide ion in the solution. So see the equation. Suppose you have taken NH, it may be KH, it may be NaH. You are treating it with water. There will be, it is very vigorous reaction. Okay, it should be done under proper with proper caution. So it is very vigorous reaction. Mh reacting with H2, it is taking the positive part of water, that is H plus, and it is forming hydrogen gas. So whenever this reaction is occurring, there will be large amount of production of H2 and hydroxide is produced. So suppose you have taken metal sodium, so hydroxide will be NaOH or KOH. So see, it is producing some basic solution. Next point, examples of complex saline hydrides. Complex saline hydrides means See, look at this formula. Lithium aluminium hydride. Now they are not like conventional formula that we have seen until now. Also by conventional I am trying to say that is NaH or KH. Now see, it is lithium aluminium hydride. They are basically, that is, we call it complex saline hydride, lithium aluminium hydride, sodium borohydride. Now these are commercially, that is commercial chemicals used as reducing agent. These are basically not direct example of ionic halide or saline hydride, but from ionic and saline hydride these compounds can be produced. And here also, if you ionize it, it is basically carrying lithium plus and AlH4 minus. AlH4 minus, if you focus on this part, it is basically containing aluminium 3 plus ion and 4H negative. So one negative charge extra which is present outside, overall negative charge -1 extra. So this is also source of H minus, just like MH or MH2, that is ionic saline hydride, actual example. So that is why we are calling them complex saline hydrides, because they are also source of H minus and they are very good reducing agent used in organic chemistry making. Okay, so this is ionic hydride or saline hydride. Next category is covalent hydride. Now covalent hydride, obviously covalent bond will be present, right? Now when covalent bond is present, the other element, in the previous case you have seen other element is alkali metal or alkaline earth metal. Now the other element, this is not very electropositive. This will be something non-metal. So they are primarily compounds of hydrogen and non-metal, in which bonds are evidently electron pairs shared by atoms of comparable electronegativities. So when there is ionic bond between two atoms, we know there is high electronegativity difference between these two atoms A and B. That is why one is completely losing electron, another one is completely accepting electron. The more electropositive, that is which is having less electronegativity, it will donate electron. For example, sodium, other element, for example chlorine, which is highly electronegative, it will accept electron. But suppose if A and B both are having electronegativity values very close to each other, in that case electrons, it is not that A is giving electron, B is accepting electron. In that case it will be equally shared between these two, and that is actually covalent bond. So here also same thing. The other element is some element which is having comparable electronegativities, and they are mostly non-metals, from elements from P block. Since most of the covalent hydrides consist of discrete small molecules that have relatively weak intermolecular forces, so they are generally gaseous or volatile liquids. In the previous case, what you have seen, ionic hydrides, they are basically crystalline, they are solid. But in this case, as the relative, there is intermolecular forces that is present between these small molecules, this interaction is very weak. So that is why they will remain as gaseous or volatile liquid. Though we have some exceptions, these two compounds. And why we are having exceptions? Because in this case, hydrogen bonding is possible. Now when there is hydrogen bonding, now the intermolecular force, you cannot say it is weak, now it is something very strong. So that is why, excepting these three, you can say in other cases they are gaseous or volatile liquids. So here, because of presence of highly electronegative element, nitrogen, oxygen, F. Basically hydrogen bonding we observe for only these three elements, N, O, F, in the whole periodic table. So these three compounds, as they are forming hydride with hydrogen, so these are the exceptions. They are not volatile, liquid or gaseous. And but rest of the compounds, you can say they are they will have this type of nature. On the basis of relative number of electrons in their Lewis structure, covalent hydride, we can do further classification. So this further classification of covalent hydride, it is based on what? It is based on relative number of electrons in the Lewis structure. Now relative number of electrons of what? It is the central element. Okay. So for example, if you take ammonia, so you have to focus on nitrogen. That is surrounding nitrogen, how many electrons are there? Is it satisfying octet or not? If you have taken water, you have to focus on the central atom, which is oxygen, and surrounding oxygen, how many electrons are there? Is it fulfilling octet or it is not fulfilling the octet? Or it may be that it is perfectly fulfilling the octet. So three possibilities are there. When octet is completely matched, that is 8 electrons surrounding the central atom, one type. If it is lesser than this, the second type, and it is more than this, that is the third type. So see, the first type is electron deficient. Now this type of covalent hydride you will get only from group 13 elements. Group 13 elements, boron, aluminium. So see, example we have taken B2H6, which is basically dimer of BH3. So in this case, if you focus on this molecule, surrounding boron, how many electrons are there? Basically, surrounding boron, there are total 6 electrons, and boron itself is having 3 valence electrons because it is from group 13, and from group 13 the general valential electronic configuration, it is NH2 NP1. Now for boron, which is from second period, N value is 2, that means it is 2s2 to P1, but whatever is value of 2, it is always having 3 valence electron. So these 3 valence electron it is using for formation of 3 covalent bonds with hydrogen, and total number of electrons surrounding boron is 6. So octet is not complete. If you take any other element from group 13, same thing will be there. So as octet is not complete, for this type of electron deficient covalent hydride, you can expect Lewis acidic type of behavior. Lewis acidic means the compounds which is having tendency to accept one more electron pair so that it can complete its octet, because octet is stable configuration. So this is the first category, electron deficient. The next category is electron precise. Now this is the category where you will have perfect, that is 8 electrons, and it is possible only with group 14. For group 14, the general electronic configuration is NH2 NP2, total 4 valence electron. If you take the example of CH4, so see there are total 4 carbon hydrogen bond. Carbon is using all its 4 electron for bond formation with 4 hydrogen. And surrounding carbon, there is basically total 4 bonds, means total 8 electrons. Similarly, you can take C2H6. C2H6 is ethane. So in this case, this is the structure. But if you focus on any of this carbon, you will see carbon is using its 4 electron for bond formation with 3 CH bond, 1 CC bond. But total number of electrons, if you see, it is basically 8. So that is why their octet is complete. And the last category, electron rich. Electron rich means now there will be excess of electron, and obviously it is from group 15 up to 17. So for group 15, the general electronic configuration NH2NP3. Then for group 16, it is NH2NP4. And for group 17, it is NH2NP5. 15, 16, 17. Elements of these groups from such compounds where excess electrons are present as lone pairs. Now we can expect their behavior as Lewis bases because they are having excess electrons. Here we have taken example ammonia and water. Now ammonia, nitrogen is from group 15, oxygen it is from group 16. So H2O, if you look at the formula, oxygen electron, total 6 valence electrons are there, NH2 NP4. For oxygen it is 2s2 2p4, but valence electron it is always 6 as it is from group 16. So 2 electrons are used for bond formation with 2 hydrogen, and rest of the 4 electrons they are present as lone pair. But total number of electrons, if we consider, another 2 is there from hydrogen. So total number it is either that is fulfilling octet or it is more than that. Okay, so such compounds where excess electrons are present, there is that is as lone pair also, mostly lone pairs, because if you consider ammonia, there is also one lone pair present. So as a result, they behave as Lewis bases. We already know that though their Lewis basicity character it may vary, but ammonia, which is very good example of Lewis base. So in this case, we can see that is ammonia is a very good base. If you are having this BH3, which is actually acting as Lewis acid, so in presence of BH3, which is Lewis acid, if you combine BH3 and NH3, then NH3 it can donate electron towards boron and it can form complex with it. So it is as if the reaction between one Lewis acid and electron rich, that is Lewis base, which is ammonia. So that is all about covalent hydrides. So this excess electron, they are present as lone pair. So for ammonia, if I consider, why I am saying it is excess, because it is not using its lone pair. So that is why it can donate this electron. So it is from second period, but if you consider element from other period, that is sulfur, and for nitrogen the next element is phosphorus, then also it is possible. So in this case, basically octet is not exceeding, but see here unused electrons are there, that is unused lone pairs are there. So that is why we are saying it is excess electron. Now octet exceeding, it is possible only for those elements where d block is present. So for example, if I am writing the next element, which is next element of nitrogen, it is phosphorus. Now phosphorus, if I am considering the molecule PCl5, then you can see there is excess of electrons. But basically we are not talking about here with any compounds with other elements. Basically we are talking about of hydrogen only. Okay, so here we have excess electrons in the form of excess lone pairs. So for pH3 also you will see there will be lone pair and there will be 3 hydrogen. So it is not that it is exceeding octet in terms of electron numbers. It is basically having some excess electrons in the form of lone pairs, unused electrons. So that is why we are saying it is electron rich. Okay. The third category is metallic or non-stoichiometric hydrides. Now metallic or non-stoichiometric hydrides, they are also known as interstitial, and why it is called interstitial, that also we will see. But try to understand that though in case of ionic hydrides also we have seen metals are there, but they are the metals from group 1 and group 2. Here also metals will be present, but they are not very electropositive metals. So these metals are not from group 1 or 2. They are basically from D block metals, transition elements. Okay. So metal hydrides are formed by dissociative chemisorption of hydrogen on the metal surface. So suppose there is metal and on its surface, this hydrogen, they can be chemisorbed. So there will be bond, actual chemical bond. That is why we are using the term chemisorption. It is not physisorption. There is two types of absorption possible, physisorption or chemisorption. But actually it is chemisorption, where actually carbon hydrogen chemical bond is present on the surface of metals at definite temperature and pressure. So it is dissociative chemisorption of hydrogen at a particular temperature. This metal hydrogen bond that can also be broken. Earlier, it was thought that in this type of hydrides, hydrogen occupies interstices in the metal lattice, producing distortion without any change in its type, leading to the term interstitial hydrides. So it is the earlier concept where it is considered that the hydrogens are basically occupying the interstices, and that is why the name interstitial of the metal lattice, and as a result there is some distortion, but without any change in its type. that is the metallic nature is still there, only the interstices there is occupation of the by the hydrogen atoms are occupying the interstices. But actually recent studies have shown that except for hydrides or some particular elements, other hydrides of this class, they are having lattice which is completely different from the metal atom, a parent metal, that is with which it is forming the hydride. So earlier concept was that as if in the metal crystal there is some interstices where hydrogens are present, and that is why there is similarity in properties with the metals itself. But actually that is not the case, though there are some exceptions. Nickel, palladium, cerium, actinium, other hydrides of this class, that is non-stoichiometric hydrides, they are having lattice which is completely different from their parent metal. Fine. So these hydrides, they show properties which is having similarity with the parent metal. So that is why this type of earlier concept was generated, but actually that is not true. Though there is similarity in properties with the parent metals, and they are also known as, for this reason, they are also known as metallic hydrides. They can conduct heat, they can conduct electricity, though not as efficiently as their parent metal. So it is true that there is similarity with the parent metals, so that is why they can conduct heat and electricity, but it is not so efficient as the parent metals do. The property of absorption of hydrogen on the transition metals, it is widely used in catalytic hydrogenation reaction. So catalytic hydrogenation reaction, very good example is if you have taken any unsaturated compound where CC double bond is present or triple bond is present, then hydrogen is used. So this reaction we have already seen in the chemical properties of hydrogen. Try to remember. And hydrogen is used in presence of some metals, palladium, platinum, or nickel, any of these metal catalysts are taken. So what is the purpose of taking these metals? Actually, what happens? There is surface of metals, and on this surface these hydrogens are attached. Now this CC double bond, they come just before, that is above of this metal surface, and these hydrogens are, this bond is broken and these hydrogens are attached to CC, and we get new carbon hydrogen bond. Fine. So this property of absorption of hydrogen on the surface of transition metals, that is PD, PT, Ni, nickel, it is widely used for this type of catalytic hydrogenation in organic chemistry. Now, why they are actually called non-stoichiometric, there is also reason for that. See, total 3 different names, though all are basically it means same thing. So we are calling them metallic hydride because there is some similarity in properties with the parent metal. Then we call them interstitial hydride, though this is the old name. Nowadays it is not used because in the earlier concept it was thought that hydrogens are present in the interstices of the metal. That is why it is called interstitial. But why it is called non-stoichiometric, now this is the reason we are going to discuss. So they are having a very unique characteristic. So what is this unique characteristic? They can be non-stoichiometric, but the fraction of hydrogen atom to the metals are not fixed. So see, look at the formula. Lanthanum, that is La, which is from F block, 4F block, LaH 2.87. So per La atom, there is 2.87 number of hydrogen atoms. Normally this type of formula we do not see, that is fraction. But this is the unique property that we can get this type of values. La, lanthanum, it is having oxidation state La3+. That is the most common oxidation state. Now, if it is 3+, the normal formula that we accept is LaH3. But see, for in non-stoichiometric hydride for lanthanum, the formula is LaH 2.87. Then for titanium, 1.5 to 1.8, the range may vary also. Then for PD, if you consider the oxidation state of PD, it is 2+, and you can expect the formula PDH2, but here the formula is completely different. So we can say they are deficient in hydrogen. So there should be 3 hydrogen, but actually there is 2.87. Then titanium, if you consider, suppose there is titanium 4 plus or 3 plus oxidation state. So formula should be TiH4 or TiH3, but there is lesser number of hydrogen. Then PDH2, but number of hydrogen is less. So they are deficient in hydrogen and non-stoichiometric. Stoichiometry is not proper. Next point, some hydrides can accommodate a very large volume of H2 as they can reversibly absorb and release hydrogen, and you can control it by applying proper temperature and pressure. So when appropriate temperature pressure are applied, some of these category of hydride, they can store hydrogen. So they can accommodate very large volume of hydrogen. And when we change the reaction condition, that is temperature pressure is not reactional condition, I mean to say when the external conditions are changed, then they can even, these hydrogens can be released also. So as if they can store, they can release. So they are very good source of hydrogen. For example, palladium can absorb 900 times of its own volume of hydrogen at room temperature. So this is very good example where you can understand how large amount compared to its own volume. It is 1:900, very high number. So this is just one example. It is also observed for other elements, mainly palladium, platinum. This property, how we can utilize it, has high potential for H2 storage. We can use it as hydrogen storage, that is as a source of energy, or it can be used as fuel, because we have already seen in the application use as part of H2. Remember, use as part we have just started in with which we have started today's class. There we have seen how H2 can be energy source. So if these metals, they can store hydrogen, obviously they are having this potential for H2 storage, which is source of energy. But their application, that is this method, it is not fully in use because some other hindrance, that hurdles that we have to overcome, but still, so that is why it is said that high potential, but it is not fully in use. So here we have this pictorial view presentation where you can see this is the metal hydride, and when there is heat applied, there is desorption. Desorption means opposite of absorption, and hydrogen gases are removed. So this is 1H together, it looks like this. Here it is in metal atomic form, only 1H, but now it is the diatomic hydrogen gas. So this is the source of H2. Fine. So this is hydride. Now related to these 3 types of hydride, we'll solve the problem. Match list 1 with list 2. In the left hand side column, we have different hydrides example: magnesium hydride, germanium hydride, B2H, that is boron, sorry, it will be B2H6, it will be 4. Then we have HF. And in the right hand side, we have the corresponding nature. So look at this, whether it is electron deficient, precise, or rich. Now these 3 are basically under covalent hydride, right? Further classification of covalent hydride, there we have seen these 3, and only one which is left, this is basically ionic hydride. Now if we look at first of all, when it is these 3 are covalent, so obviously there will be non-metal. Here we do not have any interstitial hydride, that is the last type, that we do not have. We only have 3 covalent, because electron precise, deficient, rich, all these are under covalent hydride. And this one is ionic, that means there must be group 1 or group 2 metals. Now group 1, group 2 metals, that you can find only here, MgH2, because the other elements, germanium, boron, fluorine, all are from P block, so they are non-metals. Now germanium, if you consider what is the group number, it is from group 14, it is from 13, it is from 17. Now this is obviously matching with 4, so A is 4, but what about the other 3? Other 3, germanium 14. Now 14 means it is exact electron precise, 13 is deficient, 14 is precise, and the rest of the groups 14 to 17 they are basically electron rich. So we have here boron, Ge, germanium, and we have fluorine, which is from group 17. That means GeH4, it will be electron precise, so B should be 1. It should be deficient, P2H6, because it is group 13, and this is electron rich. That means 1, 2 and 3. Now it is matching with option 4, but even if you do not consider B, C and D, just MgH2 is matching with 4, this is enough to choose this last option, because only is last option A is matching with 4. So in this way, if you are confused with the other 3, then also you can answer this question. So this is the correct option. Fine. Next question related to hydride. The hydride that is not electron deficient. So here we have, first of all, try to focus on the element actual central atom. It is silicon, which is from group 14. Here we have aluminium, which is from group 13. Then we have gallium, this is also group 13. And we have boron, which is also group 13. So all these 13, they are actually deficient. But we have to find not deficient. That means this is the correct option. Only silicon is from group 14. Fine. So next is water. So water, only physical properties, maximum structure of water will be able to finish. Only 10 minutes are there. So it is essential natural source that we all know for the existence of life, and there is it is present in adequate amount. So it is abundant in nature. Animals, plants, they require water to complete their daily metabolic activities. And also in our day-to-day life, there are some various other purposes for which we use it: cleaning, cooking, irrigation, etc. When we take picture of Earth from space, it is observed as blue, and the reason behind it is major part of Earth is covered with water. So what is the major part? It is 71% of Earth's surface which is covered with water. So 70% means it is almost 2/3, right? And the oceans hold about 96.5% of all the Earth's water, because there may be different sources of water. It is not that only ocean, it may be groundwater, rainwater, well, spring, ponds, lakes, but 96.5%, that is most of the amount, it is basically from ocean. So they are containing the large amount of water. The three main sources of water is rainwater, groundwater, which is present under the ground, that means wells and springs, and surface water. So rainwater, groundwater and surface water. And surface water examples: reservoirs, rivers, streams, ponds, lakes, etc. So these are the three main sources of water. Physical properties of water. It is colorless, odorless, tasteless liquid. We all know that. In its condensed form, that means when it is in liquid form or solid form, there is presence of intermolecular hydrogen bonding. But when they are in vapor form, there is no such thing. But only in liquid state and solid state, there is intermolecular hydrogen bonding present, and that is why it is, sorry, it will be intra, not intermolecular. It is okay. Intermolecular, there is hydrogen bond between two individual molecules. Okay. In unusual properties like high MP and BP, that is high melting point and boiling point. So normally from H2O, the melting point or boiling point that we accept. For example, if you consider the other oxides or other hydrides of group 16. Why I am considering group 16? Because in group 16 we have oxygen, we have sulfur, we have selenium. If you consider the corresponding hydride, it is basically H2O, then it is H2S, then it is H2SE. Now when we compare their boiling point or melting point, Normally down the group, what happens with increase in molar mass, it should be increased. That should be the order. But for water, there is unusually its melting point, boiling point is very high compared to its other members, that is other hydrides of the same group. And the reason behind this is this type of intermolecular hydrogen bonding. So high BP and MP, the reason behind this is hydrogen bonding. As compared to other liquids, water has high heat capacity. So its heat capacity is very high. The capacity to contain heat for long time, that is high. Thermal conductivity property, surface tension, dipole moment, etc. Everything is high compared to other liquids. And that is the reason it is having a special significance in the biosphere region. It is excellent solvent for polar and some polar covalent compounds. It is itself polar. So that is why polar compounds will obviously be soluble. But for some polar covalent compounds, polar covalent means there are basically three types: polar, covalent, and in between polar and covalent character, there are some polar covalent type of compounds. So they are also, they can be soluble. High heat of vaporization. So the heat that should be applied for a particular amount to convert it from liquid to vapor form, that is actually the heat of vaporization, or you can say enthalpy of vaporization. That value is very high, and this high heat capacity, because of these two, they help in the moderation of climate and body temperature of living beings. So as we know, our body, there is 70% of our body, it is basically water. It helps in the maintaining the body temperature, so that because of its high heat capacity, the amount of temperature, that is, sorry, not amount, the value of temperature that should be maintained for proper maintenance of other biological function inside our body, not us, animals also. This is possible for because of this high heat of vaporization and high heat capacity. So this is basically helping in the moderation of the climate and also the body temperature of animals, human beings. Fine. So here we have some properties mentioned in the left hand side column, and what are the corresponding consequences. So it is a good solvent, and as it is a good solvent, so transport of nutrients, waste products, this is possible. So for plants, they can easily take the nutrients and from water, and it is possible because all those nutrients are soluble in the water. So that is why transportation of nutrients possible. Then high dielectric constant, that means polar compounds, highly polar compounds, ionic compounds, there will be high solubility. Surface tension high. Result is physiological control factor, droplets and droplet formation, that will be easier because of high surface tension. Transparent for visible and partially for UV radiation. So that is why it allows photosynthesis even in aqueous media or plants. It has maximum density at when it is in liquid state, that is liquid water we are talking about, 4 degrees centigrade. So at 4 degrees centigrade, as its density is highest, so that is why ice can float. Okay, so they are lighter compared to water, so they can float. And isolation of water, these are basically some biological terms. Details we don't need, just remember because of this particular property that ice is lighter than water, so they can float on the surface of ice, and it is good for the aquatic animals. They can still get water under the surface of ice in cold region. High heat of vaporization controls the transfer of vapor between atmosphere and water. So and that is amount of heat that is required for vaporization process, that is actually heat of vaporization. So as it is very high, this type of control, it is better. High heat of melting, stabilization of temperature regime at freezing point or melting point. High heat capacity, stabilization of temperature. So a particular temperature can be maintained for a long time because it can store the heat, that is heat can be present for a long time because of its high heat capacity. So these are some consequences for this physical properties of water. These are so special compared to other liquids, so that is why it is having more significance compared to other elements. Fine. So here you can see physical properties of not only water, but we also have for the other isotope, that is D2O and T2O. Not all the values are there because tritium is radioactive, so all the properties data is not there. So molecular weight, obviously it is higher compared to H2O. And then melting point, boiling point. With mass, there is slight increase in MP and BP, which is clear from these values. Temperature of maximum density is 4 degrees centigrade. In terms of Kelvin, it is 277. But when you consider D2O, T2O, it is basically higher than these two. That is 284, almost 10 degrees centigrade. Maximum density possible, slightly higher for D2 and T2O, and normal density, that is also mentioned here. Vapor pressure, it is more for these two. Now why it is so? Because if you look at the boiling point, so boiling point as it is lower for H2O, so obviously its vapor pressure will be comparatively higher because these two are inversely related. Then viscosity value, dielectric constant, almost same. Enthalpy of formation, that is also it is more negative, that is more amount of heat will be released in case of D2O. Enthalpy of vaporization, it is higher for D2O, slightly higher. Enthalpy of fusion, that is also slightly higher. Electrical conductivity, these data are not present, only for water. So from these values you can compare these three, and question regarding where these values will help you to solve the question. So that is why exact values I am not saying that you have to remember, but what is the relative, that is whether it is higher for H2 or D2O. This information is important. For example, if you consider enthalpy of vaporization, it is slightly higher for D2. Okay. Then boiling point, it is slightly higher. Melting point slightly higher. So these are the little information that may help you to solve a specific type of problems. Okay. So we will end here. We are ending at physical properties of water. Next day we will see structure of water, chemical properties of water. So thank you for listening. We are ending the session.